Welcome back, Algebra 2 students. This is 8-4 Infinite Geometric Series Part 2. The first video had us talk about what an infinite geometric series is, and then also the formula for finding the infinite sum. And then this time, we're going to take a look at the second part of your note sheet that has you try the practice problems. So let's take a look at those. All right, let me pull up this. All right, so if you're just tuning in, we did the warm-up, reviewing 8.2 and 8.3, and then we figured out by finding finite sums that if we have a geometric, and again, this only works for geometric series that also have a ratio less than 1, which means it was like an exponential decay type of scenario. And that means that the terms are fizzling out to about 0. So we get to a point where we're adding some significant numbers, and then towards the end, the terms become about 0. And so since the terms kind of fizzle out, we get a number, and then we're adding 0, and about 0, and about 0, and about 0. So we're kind of just left with that number. So we did this example, and we estimated the sum of all the terms, and we said maybe it's about 1, and then we found this formula. So just going back to that real quickly, if we're using this finite, or I'm sorry, let's say that again, infinite, because it has this infinity here, infinite geometric, so you can see our geometric scenario, series where the ratio, this 0.1, is less than 1, we can find the infinite sum by taking the first term over 1 minus the rate. And so now that we know this is s sub infinity, not n anymore because it's not finite, this is infinite. And we said in this case, the first term was 0.9, and we can find that by plugging 1 into the equation. I say this equation, the terminator, the equation or the rule that gives us the terms. And we get 0.9. And then over 1 minus the rate, which in this case was 0.1, and that actually does give us 1. So we figured this out, and we tried a couple, and then I asked you to try a few on your own. So let's see how you did. So we first look at this scenario, and I say, okay, this is an infinite sum because of this infinity on top. So in order for us to even be able to do an infinite sum, we have to have a couple of things. We have to have it be infinite geometric. So I've got an a, b to the x. So this tells me, yeah, okay, we're geometric. And the rate, though, so this is geometric, but the rate has to be less than 1. So let's check. Is the rate, the absolute value of the rate, less than 1? And when I say rate, I'm saying ratio. And we can see right here, this is our ratio. Is the ratio less than 1? It is. So we've got infinite, right? That's kind of our key concept here. We have 1 that it's infinite. 2, it's geometric. And 3, the ratio is less than 1. So if those three things are true, we can use our infinite sum formula. All right, so our infinite sum formula says we need to find the sum of this infinite series. We need the first term over 1 minus our rate. All right, so the first term, how do we find the first term? Well, the first term, we have to plug 1 into our terminator, right? We said this is like our terminator, and this equation down here is like our summinator. The terminator gives us the terms, and the summinators, the equations to give us the sum, give us the sum. Right? All right, so the first term is going to be found, we're going to do 5 times 1/2 to the first. And so the first term is actually going to be 5/2. this one. All right, so it's not just 5, because in this scenario, when I plug 1 in, we see that the first term is actually going to be 5 halves. All right, so I have 5 halves. And then over 1 minus our rate, and our rate here was 1/2. All right, so then that gives us, keep this going in an equation. That gives us a keep it, change it, flip it. So I've got 5 halves, keep it, change the division to multiplication. And if you notice, 1 minus 1/2 is actually still 1/2, right? 1 minus 1/2 is 1/2. So 5 halves divided by 1/2 is going to be 5 halves times 2 over 1 technically, which gives us 10 over 2, which is 5. And that's our sum. Now, that's not this 5. That's just kind of a coincidence. The sum is 5, right? Just because what happens is the terms eventually fizzle out to 0 because it's an exponential decay scenario, and we get a sum of 5. All right, so let's try the next one. Let's see how you did. So I see, oh, okay, we're infinite again, and it does look geometric, but we have to check to see if the ratio is less than 1. So we have to be careful because we're going to want to try this formula. It's so cool. And we just can't jump into the formula every time we see an infinity, right? It could be an arithmetic. If it's arithmetic, that means we're adding constantly or we're subtracting constantly. And so what that means is that we're not going to have terms that fizzle out. We're going to go to positive infinity or negative infinity, and then our sums will do the same. So if this doesn't work for arithmetic. It works for infinite, geometric, when the rate is less than 1. So for all of these problems, if you just jump into the formulas, it's not going to work out for you. You have to do the check. Is it infinite? Yes. Is it geometric? Yes. But is this rate less than 1? Nope. 5 is not. It's greater than 1. So we'd say no sum. It didn't work for our criteria. It didn't fit our criteria to use the sum for an infinite series, so we can't do that one. All right, let's try this one. Well, this is geometric and the rate is more than 1, but I'm not going to say no sum because this isn't an infinite sum. This doesn't have the infinity symbol like the previous one. This one says 6. So that means this isn't going to be the infinite sum formula. Instead, this is going to be the S sub n formula when we have the number of terms being 6. So what I'm going to do is I'm going to use that formula. If you remember, that is our first term. Let's put this like this. So this is our first term. Let's see if I can write here. 1 minus the rate, and just that r is to the nth power, over 1 minus r. All right, so then for us, the first term here, well, how do I find the first term? I have to plug 1 into the formula. And when I say formula, I mean the rule, the terminator, the equation that gives us the term. And so 5 to the first is 5. 5 times 1/2 is 5 halves. So our first term here is 5 halves. And then I can multiply this by 1 minus, our rate this time is 5 to the 6, because we have 6 terms going on here, right? 1 to 6, over 1 minus 5 again. And so for this one, we can actually do this infinite sum. You have to be really careful when you're typing this into your calculator. I'll see if I can kind of show you. You take your calculator, and you need to type everything in with careful parentheses. So I might actually do 5 to the 6th, or to the 6th, right? I don't know if you can see, that might be dark, but 5 to the 6th, 1 minus second answer, that number. And then I can divide that. Oops, divide that by 1 minus 5, and then multiply that by 5 divided by 2. All right, so then in this case, I got 9,765. So you can see this is a big number. It is growing, right? And so I can try that one more time just to double check. 5/2 times parenthesis 1, I kind of do a sub parenthesis, 1 minus parenthesis 5 parenthesis to the 6th. And then parenthesis there, divided by parenthesis 1 minus 5, parenthesis, and yep, there we go. So I'm gonna kind of see if I can zoom in so you can kind of see how I type that in with parentheses. Let's get there maybe like that so you can see how it's typed in. And that's how we get our sum for a finite. So we have to be careful when we're plugging things in, right? When we're checking to see, is this arithmetic or geometric? And then is it finite, meaning we have an ending number, geometric? Well, then we have this finite sum formula. Is it infinite? Well, then we only can use it if the rate is less than 1. If the rate's bigger than 1 and it's infinite, we just say no sum. All right, so there's a couple more. So here we see 2 to 5. So I'm thinking, okay, am I adding the same amount each time? Is this arithmetic? Nope, but it does look like I'm multiplying each time by something. And to find that, I can always take, again, the second term divided by the first term. And then I just make sure that if I do multiply it, like as we go, it should still work. So we find out that our rate is 5/2. And then if I do 5/2 times 5, I would get 25/2. If I do 25/2 times 5/2, I would get 125/4. So it does work. Now, I see the dot, 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 so it actually is infinite because of this dot, dot, dot. That means I see that it's geometric because I'm multiplying by the same ratio each time. It is infinite, but I can't use the infinite sum formula because the ratio here, right, this ratio, it's greater than 1. It's like 2.5, right? So 2.5 is more than 1. So in this case, I'd have to say no sum. I can't use any other formulas because we only have, like for infinite geometric, we can only use that formula, but only if the ratio is greater than, or is if the, we can only use it if the ratio is less than 1. Here, it was more than 1, so we can't do it. All right, let's try this one. I see 10 and 5. Am I subtracting 5 each time? No, so it's not arithmetic. Am I multiplying by something each time? Yeah, here it looks like I'm multiplying by 1/2. And again, I can do 5/10, and that gives us the 1/2. So here I see the ratio is 1/2. So it is geometric. The ratio is less than 1, and they do want us to find an infinite sum. So here, ding, 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 we have a winner. We can do the infinite geometric formula because it is geometric, it is infinite, and the ratio is less than 1. So I can do the first term divided by 1 minus the rate. And then in this case, that's going to be 10 divided by 1 minus 1/2, which is going to give us 10 divided by 1/2, because 1 minus 1/2 is 1/2. And I have to keep it, change it, flip it. So we're going to get 20. All right. So here's an example of 2 geometric series, in fact, 2 infinite geometric series, but we could only find the sum of the second one because the ratio was less than 1. All right, so in sum, no pun intended, well, actually pun intended, in sum, we have learned in 8-2 that we have a special arithmetic sequence, and to find the sum of an arithmetic series, we can only do that if it's finite, meaning we find it from one term to another term. So we have an ending, we've got this formula. Geometric finite, well, that's 8-3 where we learned about geometric sequences, which then brought us to geometric series when we actually start adding things. And here was our formula for geometric finite. And then finally we end here with 8-4, which says, hey, there's a special situation where if geometric is infinite and the ratio is less than 1, well, we have a geometric series that operates kind of like exponential decay, which means the terms are going to fizzle out. And so when we think about sums, eventually we're going to be adding just like about 0, about 0, about 0. And so we can get a sum. And so our infinite sum, notice that we had finite has an n, finite has an n. Here, either it's just plain s or an infinity symbol. It's the first term over 1 minus the ratio. Well, that's the end of 8-4 Infinite Geometric Series Notes. Thanks for following along, and good luck with the practice. All right, let's see. Stop sharing. All right. Thanks for watching.